Hello everyone, Miss Aguilar again. This is the second part of the video, or the second video on Unit 1 worksheet for calculating velocity and speed. We're on problem number 3. It reads, which object has a greater velocity, a ball rolling down a 3.4 meter hill in 6 seconds, or a fish swimming upstream and covering 5.4 meters in 0.4 minutes? So this problem just has you comparing two different velocities. First, you have to solve for the velocity for both of them. So it's the same way as we did before. Always start off with the starting equation, do a list of knowns and unknowns, and then plug in chug. So our starting equation is delta x over delta t, and velocity for the, hold on, let me erase that. Velocity for the fish is equal to delta x over delta t, and then velocity for the ball is delta x over delta t. Same equation, variables will be different. So we have velocity, which we're solving for, and we have xf, xi. Remember, that's what the delta x is. The delta x is just final minus initial position. And then total time. We're going to go with total time here because it gives us a total time. We're not going to worry about changing the time. But I did put xf and xi here because I wanted just to touch on something before we, go on. Anyways, here we go for the fish variables. xf, xi, and total time. All right, so let's look at the values for the ball. The ball rolls down a 3.4 meter hill in 6 seconds. So our time is 6 seconds. And when it gives you just a total kind of, you can call it distance, but it's really displacement, a total displacement, if it doesn't give you an initial position, you have to assume the initial position was 0. And if you want to follow exactly how we have these equations, xf minus xi, you should. So just assume the position is 0 if it's asking you to solve for velocity and they don't give you an initial position, but they give you a displacement instead. They give you like the total displacement. So our initial position is going to be 0, and it rolls down to 3.4 meters. So he ends up being displaced 3.4 meters. All right, and then for our fish, again, initial position, we're assuming 0 meters, and he covers 5.4 meters. So his final position will be 5.4 meters. For the fish, his total time is 0.4 minutes. Now remember, we need to deal with seconds in our units for velocity. So 0.4 minutes in seconds is just 24 seconds. And how did I figure that out? I just took 0.4 minutes and multiplied it by 60 because there are 60 seconds in a minute. Okay, so then we plug in chug. Delta x over delta t for our ball, so 3.4 meters minus 0 meters over 6 seconds. And I put that in, and I ended up with a value of 0.566667. I'm going to just put 0.57 meters per second. Rounded. So there you go. That's the velocity of the ball. The velocity of the fish. Okay, so plug and chug, right? So 5.4 meters minus 0 meters over 24 seconds. I ended up with 0.225. So 0.225 rounded is just 0.23 meters per second. So velocity of the fish, 0.23 meters per second. So the question asks you which object has a greater velocity. Well, look at them. The fish. I'm sorry. The ball. The ball has a much greater velocity. Okay. Let me just erase this real quick so we can see the next question clearly. Okay, so in the qualifying round of the 50-meter freestyle in the sectional swimming championship, Charlie got an early lead by finishing the first 25 meters in 10.01 seconds. Charlie finished the return leg 25 meters in 10.22 seconds. First, determine Charlie's average speed for the entire race. So we're doing speed and total distance. And next, determine his average speed for the first 25 meters. So total distance would be 25 meters. And then determine his average velocity for the entire race. So the displacement and, average velocity. So let's set that up. So for A, we're going to use the total distance. Speed is equal to D over T. B is, again, speed is equal to D over T. And then for C, it is velocity is equal to delta X over delta T. So for A, it is his total, and the entire race. So let's list our knowns and unknowns. The entire race was 50 meters. His total time was 10.01 plus 10.22. So that ends up with 20.23 seconds. So let's plug and chug for A. We have 50 meters, which is our distance, over a time of 20.23 seconds. I put that in my calculator and I got 2.47 meters per second. So his speed for the entire race was 2.47 meters per second. That was his average speed for the 50 meters. The next one is asking again for his average speed, but for the first 25 meters. And it says here that the first 25 meters he was able to complete in 10.01 seconds. So our time is 10.01 seconds, and the first leg was 25 meters. So again, we're going to put D over T for our speed equation. We get 25 meters over 10.01 seconds, divide, and I have a value of 2.497502. So let's just call it 2.50 seconds. Or I'm sorry, 2.50 meters per second. So that is his average speed for the first 25 meters. Okay, now let's look at velocity. We have V, which we're solving for. Delta X is just XF minus XI over T F minus TI. So what's his initial position? His initial position is 0 meters, right? Because if you think about it, where can I draw this little swimming picture? Here, let's put it right here. Okay, if he is swimming, let's pretend we're looking down at him. He's swimming out 25 meters, and then he swims back here. So his start and his finish, or you could say his initial and his final, are both here. And we could call this 0 meters. We could actually call this 25 meters if we wanted. We could call it 50 meters if we wanted. But regardless, he starts and he finishes in the same spot. Okay? So his initial position is 0 meters. His final position is 0 meters. His final time, right? So he goes out 25, he comes back 25, and it's 10.022 seconds. And his initial time is 10.01 seconds. So we could put all this in, but just look at these two values right here. These equal 0 meters. So anything divided by 0 is just going to equal 0. So our velocity for this is 0 meters per second. I didn't go any further because I just see that 0 and I know it's going to be velocity of 0 meters per second. So a couple of you are probably thinking, well, wait, what about the last problem? How come we didn't use 0 as our initial position there and we're using it here as 0 meters? Well, you could use 25 and 25 as his initial and final position, but in my mind, as I'm thinking about this, it's kind of like the racetrack, right? except it's not an oval. You're starting and finishing in the same place, where the retriever, right, he was starting and finishing in a different place. So we considered that final and initial position differently. If he starts and finishes in the same place, then you can call it whatever you want. It wouldn't matter. If we called this 25 meters and 25 meters, we would still end up with 0 meters. Okay, let's do number 5. A bus travels at 280 kilometers south along a straight path with an average velocity of 88 kilometers per hour. To the south, the bus stops for half an hour, then it travels 210 kilometers south with an average velocity of 75 kilometers an hour to the south. How long did the total trip last? Okay, so here we're using our equation to solve for time. And if you remember, time is just delta x over v. And what's going to happen is that you're going to calculate the time for 2 stops, right, or 2 stretches, and also include the fact that it stops for half an hour. Add all 3 of those times up, and you'll end up with the how long did the total trip last. We're considering all of this one total trip. So the first part is t, and we're going to figure that out. Delta x, remember we have to assume that he has an initial position of 0, so his total distance traveled was 280 kilometers, and velocity, his velocity or her velocity, whatever, was 88 kilometers per hour. And then he stopped, right, for 0.5 hours, so time here. And then the next, or the last part was, again, we're solving for time. Total displacement was 210 kilometers. Remember, we have to assume, I'm going to say this again, that this initial position was 0 meters, or 0 kilometers, and then final was 210. So displacement is 210. Plus, I think it also says, yep, along a straight path. So along a straight path, remember, if we're going in a straight path, our displacement and our distance are the same. And I'm not switching these to meters per second because everything is already in the same units, kilometers per hour. We still have units of distance and we still have units of time, okay? So we're just going to leave it like that. And the velocity for this third part was 75 kilometers per hour. So then we plug and check for both of these. We'll end up with time and add them all together. So we'll end up with a total time. Okay, so 280 over 88. And I end up with 3.18 hours plus 0.5 hours, right? And then we have 210 kilometers over 75 kilometers per hour. And I end up with 2.8 hours. So if I take, this time, sorry, it's getting messy, and this time, and this time, and I add them all together, I end up with a total time of 6.48 hours. Again, you don't have to convert this to meters and seconds. It's okay. All right, I have like 1 minute to explain this, you guys. Let's see if I can do it. Okay, so what you're going to do here is you're going to convert hours into seconds. This ends up being 7,200 seconds. And then 9 minutes into seconds, which ends up coming out to be 540 seconds. And then you have 20 seconds. So you're going to add all of this together, and you end up with a total time of 77:60. And then you're going to divide it, or no, you're going to multiply that by a rate of 5.436 meters per second, and you end up with about 42 kilometers. All right, I have to end now. I have 6 more seconds. I hope this is helpful. Email me if you have questions.